Hello, in this tutorial we will take a quick retake of points on virtual work that we discussed in tutorial number 1 and we will continue with few typical problems related to finding supports in support reactions in a beam and one or two problems on finding the resultant of concurrent force system. And the very important point about the application of virtual work lies in applying the principles of zero work to the systems that are in equilibrium. That means the algebraic sum of work done by all the forces acting on a system that is already in equilibrium should be equal to zero for a virtual displacement that is being given, and this virtual displacement that is given will be consistent with the kind of the system and kind of supports and kind of movements that would happen in the absence of equilibrium. Therefore, we will go through the problems very quickly, and the fundamental thing about this is the virtual work. The sum of the work done in the system should be equal to zero, provided if the system is in equilibrium. So the first problem is about finding the resultant, and here are the forces: 120 Newton, 200 Newton with various inclination. This comes with a slope of 1:2 and this comes with a slope of 4:3, and we will find out the angle of inclination over here. This is what to be theta 1, then tan theta 1 equal to 1 by 2. Therefore theta 1 equal to tan inverse of 0.5, that is 26.56, and on the other hand tan theta 2 is 4 by 3 opposite by adjacent, and we will get theta 2 equal to 53.13. So having gotten all the angles and all the forces, we have to, since the equilibrium, the virtual work concept, the virtual work principle is applicable only for the systems in equilibrium, we will superpose an equivalent over here, equilibrium over here, and we will just tend to equate this particular system to be in equilibrium, and this is the equivalent. Let the system be in equilibrium with the presence of equilibrium, and we know the resultant is just opposite of equilibrium but same in magnitude. Therefore this equilibrium is inclined at an angle of theta, and we will just find out, and we will just give the displacements over here, positive virtual displacements dx to the right of O. So O dash will be over here horizontally, and O dash will be there vertically up with a virtual displacement, small virtual displacement of del y vertically. So therefore we have presumed positive virtual displacements horizontally and positive virtual displacement vertically, and we will resolve all the forces into horizontal components and vertical components and multiply with this positive displacement that we have given forcefully, assuming that the system is in equilibrium, and the sum of the works done should be equal to zero. Therefore first of all we will move with horizontal components. Let the algebraic sum of work done in moving the point O by del x equal to 0. Therefore we will resolve the forces, and 200 cos 26.56, because this is right, the component of 200 Newton horizontal component is to the right, which is positive, and del x is also positive. While 120, you will have the horizontal component going towards left with an angle 53.13. Therefore this is 120 cos 53.13 into del x. Del x is positive, but force component is negative. And here again 50 cos 60 is also negative, going towards the left coordinate axis. So 50 cos 60, so this becomes negative, this work becomes negative owing to the negative force, into del x, plus 100 sin 40, because angle is referred with respect to vertical. 100 sin 40 is positive because the force is going, the component of the force is going rightwards, into dx, and e cos theta, this is equilibrium into cos theta, that is also positive, and del x is also positive, equal to 0. Then if we separate the del x as a common factor, and if we have the multipliers within the brackets, within the parentheses, we will get this particular equation. Now del x cannot be equal to 0 because we have introduced this virtual displacement, small virtual displacement. Therefore it cannot be equal to 0. Therefore the things within the bracket must be equal to 0. So upon simplification of all the numerical terms over here, we will find minus and send e cos theta that side, it becomes minus e cos theta, and evaluate whatever that is there numerically over here, it will give us minus e cos theta equal to 146.2 n. So this is one. Algebraic sum of work done in moving the point O by del y equal to 0. So del y is going up and it is 200 cos. So we will just quickly go through the figure before we write this. So 200 sine 26.56 going up, which is positive. Displacement is also positive. 120 sine 53.13 positive. Displacement is also positive. Del y. And this is, as far as 50 Newton is concerned, it is 50 sine 60 negative, but the displacement is positive. Force is negative. And here once again 100 cos 40 is negative and the displacement is positive. So this culminates in this equation for the horizontal, for the vertical component now. And yeah, here it is. Algebraic sum of work done in moving the point O by del y equal to 0. Therefore 200 sine 26.56 into del y, 120 sine 53.13 into del y, minus 50 sine 60 into del y, minus 100 cos 40 into del y, plus e cos theta, e sin theta I should have been, sorry, yeah, e sin theta. Yeah, we'll just change it quickly. E sin theta. So this is the consolidated equation, and we will just take out the common factor del y, and this is the expression that we are going to get, and we will send e cos theta that side, so that we will have e minus e cos theta, and we will just simplify all these things within the bracket, and we will get minus e cos theta equal to 65.5. Now we have two equations. Minus e cos theta equal to 146.2, minus e sin theta equal to 65.5, and we know fully well that sigma fx is r cos theta, and it is here r cos theta. The horizontal component of the resultant should be equal to the horizontal component of the equilibrium with a negative sign. Therefore r cos theta equal to this much, and in the same token r sin theta equal to this much, which is equal to minus e sin theta. Therefore r equal to square root of 146.2 whole square plus 165.5 whole square, because if we square this, e square r square into cos square theta plus sin square theta, that will become 1, and what we will be left with, 146.2 whole square and 65.5 square, and we will, if we want to get r, we will take the square root and we will find the resultant, the way we used to do earlier. Then theta equal to tan inverse of r sin theta, that is sum of the vertical components, work done by the vertical components, it is 65.5 divided by 146.2, so we will get 24.1 degree. So this is how we resolve any, we solve the problem related to any concurrent force system by principle of virtual work. To repeat the method, we will just give a horizontal displacement, positive horizontal small displacement of del x, and vertical positive small displacement, virtual displacement of del y. Then we will assume the equilibrium, because virtual work principle is applicable only for the systems that are in equilibrium. Then we will solve in the similar way that we used to solve a concurrent force system resultant, but with a difference, and we are equating work to 0. Right, we will go to beam now, beam problem. To find the support reactions in the loaded simply supported beam, like this is a simply supported beam, and here since the beam is loaded with vertical load, it doesn't matter whether at A there is a roller support or a hinged support, because hinged support comes into effective if and only if there is a inclined force, and if and only if there is a horizontal component of the force. Therefore this is the system. Now we need to find out the reactions. Therefore we have to give a small, this is a system which is in equilibrium, and it is readily amenable for the analysis under the virtual work principles. So give small positive virtual displacement over here. That means you hold it here, we are not supposed to give any displacement over here, and it should be just lifted by a small amount del y, thereby inducing kind of a virtual displacement. Now the entire beam moves up in this particular fashion, and there is a corresponding displacement proportional to dy, some percentage of dy going over here vertically up. There is also a proportion of the displacement that will happen over here under the load 40 kilonewton. Therefore we need to find out what is del yd as in terms of del y and del yc in terms of del y. And this is what we need to find. Then we will just reduce the number of unknown to only del y and rb. Now we can find out del yc by comparing similar triangles. Here is a small triangle with a height del yc and 2 meters as the base, and del y we know, which has been induced. This particular virtual displacement has been induced, and this is the big triangle with the base 2 plus 4 6, 6 plus 2 8. Therefore del yc of small triangle divided by 2 equal to del y divided by 8, and we will get del yc equal to 0.25 del y. And in the same token, we can also find del yd to be 0.75 del y by comparing. So del yd divided by 6 equal to del y divided by 8. So it becomes 6 by 8. It becomes 0.75 del y. So now, after having known the various displacement, we will just multiply in order to equate work to be equal to 0. Applying virtual work principle, total work done by the forces equal to 0. RA into 0, because the support A has not undergone any virtual displacement, minus 40. This minus 40 comes from the fact that the load is acting vertically down, but while this is positive, 0.25 del y, and minus 80 into 0.75 del y, and this is rb into del y equal to 0. rb into del y we have just induced, and here we have computed the values of del yc, del yd as a function of. So this is minus 40 into this value, minus 80 into this value, and this value should be expressed as a parameter involving del y, because we want to reduce the whole lot of unknowns into only one unknown, that is del y. So del yd expressed in terms of del y, del yc expressed in terms of del y. Once again it is over here. Then we will just multiply. That's all. The loads are negative, but the displacements are positive. While rb is positive because it's going up, and displacement is what that we have given. Therefore, when we equate this is the virtual work principle, and this will just vanish. Minus 40 into 0.25 minus 80 into 0.75 plus rb into del y equal to 0. We have taken del y as the common factor. Del y cannot be 0 because we have only introduced this in order to solve the problem. Therefore, upon simplification, we will get rb equal to 70 kilonewton. To find RA, again, we need to induce a virtual displacement, small virtual displacement in the positive direction at A. So we need to provide a positive virtual displacement at A. We have done this. Upon doing this, it will be lifted up and it goes positively up, and we need to find out what happens, what is the amount of proportional displacements that happens beneath this load and beneath this load at C and D. It's once again by comparing similar triangles, and we need to find out this relative displacement. So as far as del yc is concerned, del yc by 6, this is the triangle including the base. So del yc by 6 equal to del y by 8. Del y is here and 8 is over there. That is a big triangle. Therefore we will get del yc equal to 0.75 del y. In the same token, we can also compare del yc by del yd by 2. Yeah, del yd by 2 and del y by 6 by 8, sorry. Yeah, same thing we are doing over here, and we will get del yc as a parameter involving del y. Therefore we have reduced the 3 unknowns into only 1. So applying virtual work principle, total work done by the forces equal to 0. RA into del y, that's what we need to find out, minus 40 because it is acting down into 0.75 del y, minus 80 into 0.25 del y, plus RB into 0, because at RB there is no displacement whatsoever, so equal to 0. And upon simplification, its RA del y is taken out, and del y cannot be equal to 0 as a multiplication parameter, because we have introduced this virtual displacement vertically up positive. Therefore this has to become 0, the things under the brackets, and we will get RA equal to 50 kilonewton. We can make a small check. Sigma Fy should be equal to 0 according to principles of equilibrium. We have RA plus RB going up, 40 plus 80 coming down, it will get us 120 kilonewton. And if we add this RA that is obtained through virtual work method, and RB which is also equal to 70 kilonewton, so 70 plus 50 becomes equal to 120. That's how we can also get a check as to whether we have done the problem correctly or not. Now find the support reaction at B for the beam loaded as shown. So here is a concentrated load. So this particular problem is a little different when compared to the previous one. It has by just only one small change, and here we have a UDL. And as we have understood before, that UDL cannot be directly handled anyway, it should be converted into equivalent concentrated load. The value of equivalent concentrated load is the intensity of the load into the spread over which it is being placed. It is 20 into 360 kilonewton acting right at the center. Therefore we will give a small vertical displacement, virtual displacement of del y positively, that is up. So give a small positive virtual displacement here at B, then the entire beam is lifted, and here there is no virtual displacement. So we know there is a proportional displacement beneath C and beneath D, beneath the loads. So we need to compute this by comparing similar triangles. Del yc by 1 of the small triangle equal to del y by 3 plus 2 5, 5 plus 1 6. Therefore del yc equal to 0.17 del y, because 1 by 6 is 0.17. Now in the same token, del yd by, this is 1.5 from here till here, because this is 3 meters, 1.5 plus 2, 3.5 plus 1, 4.5. So del yd divided by 4.5, the base of this triangle here till here, so equal to del y by 6. So 3 plus 2 plus 1, 6. Therefore del yd equal to 0.75 del y. So now we need to multiply RB into del y plus 60 minus 60 into del yd minus 40 into del yc equal to 0. So sum of the works done by the components, by the forces in the system should be equal to 0. The system being in equilibrium. Right, so we have got 0.75 del y over here, and we have got 0.17 del y over here. We can readily use this into our equation, applying the virtual work principle. Total work done by forces equal to 0. So RA into 0, no virtual displacement. RB into del y, which is positive, minus 40 owing to the force coming down, into 0.17 del y, minus 60 into 0.75 into del y equal to 0. So if we, upon taking out the common factor del y equal to 0, and we cannot equate del y equal to 0 because it is an induced virtual displacement. So we will get RB equal to 51.8, and find the reaction. Suppose so we'll go to the next problem. RA, for RA we need to lift the beam up at A. That's all. Same thing is to be repeated. And of course we should be very careful in finding the appropriate proportionate displacement that would happen beneath every other load, because we will be lifting the we will be giving virtual displacement only at the supports where the unknown is. Find the support reaction at B for the beam loaded with moment. So here there is a moment, and here there is a vertical force. If we quickly recall, as far as the force is concerned, with the force, the work done is force into the displacement along the direction of the force. And as far as moment is concerned, moment into the value of the moment into theta will be the work done by the moment. So give a small positive virtual displacement here at B. So this is A, this is B, let us say. And so we will just write it down for the sake of clarity. This is A and this is B. Yeah. Now we'll just move on. Okay, So we will just give a vertical displacement at B. So beam will get lifted, and here is the proportionate virtual displacement that happens at C, which can be computed using by comparing similar triangles, right? So it is del yc by 1 of small triangle, del y by 6 of the big triangle, and we will get del yc equal to 0.17 del y. Now del y, as far as theta is concerned, equal to minus 6 theta, minus 6 del theta, because this is del theta which is going in anti-clockwise direction, while if we lift the beam up by del y, it is also going to rotate in anti-clockwise direction as far as moment is concerned. So as far as the effect of moment is concerned, that is seen in the form of rotation. Therefore del y equal to minus 6 d theta. Okay, d theta is negative. 6 comes from the span of the beam. It is something related to what is that, the segmental length of a given circle of radius r. If radius is r, and if a segment subtends an angle of theta, the length of the segment is r theta, and here the radius is the span of the beam, and theta is the rotation that has happened, and delta s, the segmental length can be equated to delta y, though it is curve natured, and here it is straight. Since del y is very, very small, we can always apply the principle of a geometry of a circle, that is del y equal to r theta. Instead of r theta, we would say the span of the beam, that is 6 theta, 6 del theta it is, but del theta is anti-clockwise, therefore it becomes negative. So this becomes negative owing to the negative kind of a rotation, because we had sign conventions in the very first tutorial. Positive clockwise moment is positive and clockwise rotation is positive. Anti-clockwise moment is negative and anti-clockwise rotation is negative. Rightward force is positive, leftward force is negative, and upward force is positive and downward force is negative. And therefore upward displacement is positive and rightward displacement is positive. These are all the positivity and negativity of the deformations of the virtual displacements as well as forces respectively. So so we have estimated del yc equal to, in terms of del y, it becomes 0.17 into del y. Now del y is also equal to minus 6 del theta. Now therefore del theta equal to minus 1 by 6 into del y minus 0.17 del y. So we have expressed del theta also in terms of del y, so that whenever moments comes into picture, we will just multiply this. So that will become the work done by the moment. So work done by the moment is moment into theta, and theta here is converted into linear measure in terms of del y. Right, applying the virtual work principle, total work done by the forces equal to 0. Here force will also include the moment. Now we will see RA into 0, because we have not induced any virtual displacement over here, and RB into del y, this is the virtual displacement that is being applied, minus 40 into 0.17 dy. This has been calculated, the proportionate virtual displacement at C, and minus 40 because the load is coming down, minus m. Here moment is positive because it is clockwise, but del theta is negative because that is anti-clockwise. So here there is a negative sign. Now we will replace this del theta by del y. We have already found out it is 0.17 del y, and all other things are known. RB minus 6.8, the simplified values of this thing, and this is the simplified value of 30 into 0.17 into del y equal to 0. Del y cannot be equal to 0, therefore RB minus 6.8 minus 5.1 equal to 0. Therefore we will get RB equal to 11.9 kilonewton. And if you want to find out reaction at A, we need to lift the beam at A to the little extent, to the positive extent, virtually. Therefore, to find the reaction at A, assume a small positive virtual displacement of del y over here. It's over here. Now the beam will rotate like this. So as far as rotation is concerned, it is positive. Earlier it was negative. Since the rotation is clockwise, it becomes positive. Here moment is also clockwise and the rotation is also clockwise. Therefore work done is also clockwise. Only we need to find out what del theta, how del theta relates to del y, okay, given the span of the beam. So del yc of the small triangle divided by 5 from here till here, it is 3 plus 2 5 equal to del y by 6, and we will get del yc as a function, as a parameter related to del y, 0.83 del y. It becomes 5 by 6, 0.83. And on the same token, del y equal to r theta. R means span over here, r is 6 into del theta. Therefore del theta is 1 by 6 into del y. 1 by 6 is 0.17. So we know the displacement owing to the vertical load and owing to the moment, and we will just multiply them and we will equate the work done by the forces equal to 0. So RA into del y, this is where we have lifted. RB into 0, there is no virtual displacement. Minus 40 into 0.83 del y, minus 40 because the load is coming down again, plus m into del theta. M is also positive, del theta is also positive. So we replace del theta with 0.17 del y. So now this is the expression, and del y cannot become equal to 0. Therefore this expression should be equal to 0. And what we get is the value of RA is 28.1. RB is previously we have evaluated to be 11.9. So 11.9 plus 28.1 make it 40, and the applied load over there is also 40 because RA plus RB equal to 40, and we have calculated separately RA and RB using virtual work principles. So friends, dear viewers, with this we are going to close the tutorial 2 on virtual work principles, and we will just come up with little complicated problems in our third tutorial. Until then, bye, and if you have liked this video, kindly subscribe to my